Hello, in this video, I'm going to talk about first order reactions. The bulk emphasis of kinetics is going to be on first order reactions. So this video is going to be more lengthy, more thorough, give you more examples, and in the description of the YouTube video, you can find links to some other worked problems on my channel. So a first order reaction is again going to be the main focus of your college chemistry courses. It explains radioactivity. It describes most drug metabolism. And when you get into biochemistry or organic chemistry, many reactions are first order and second order. So the general reaction again is A goes to B. It doesn't matter what the coefficients are here. The rate law is expressed as rate is equal to the concentration of A to the first power. That very simply can be written rate is equal to K times A. All right. If you have time in the first column here and then concentration in the second column, this is francium-224, which is a radioisotope. It's radioactive and it spontaneously decays over time and goes away, right? It converts to something else you'll see on the next slide. If you were to graph this data, you can see how it's not linear, okay? The amount, either the concentration or the moles or the milligrams or grams or whatever amount of francium-224 decreases exponentially, okay? At first it's decreasing fast, and then over time it's getting less and less and less, okay? So the rate of decomposition is very high in the beginning, and the overall rate of decomposition by the end is very slow, okay? Now you have this idea of half-life. This is very, very important, okay? The half-life is defined as the amount of time for 1/2 the material to react. So if you look at this table here, you can see that 0.120 is half of 0.240, and that happens after 200 seconds, okay? So that's 1/2 the material there, okay? And so you can also calculate the half-life, which is equal to the natural log of 2 over k. Again, we have that ln function, which is the natural logarithm, and it should be a key on your calculator. Look around for it, okay? Now, it doesn't matter which pair of data. You can see when you're going from 400 to 600, that's a passage of 2 seconds. You also decrease in concentration or amount by 1/2, okay? So the half-life there is 200 seconds, okay? Now, for a first order reaction, you can plot a different quantity, and that's the natural log of francium-224 versus the time, and that right there is going to be linear, okay? And you can see a plot of that right here on the board. That's the same data, and the slope of this is going to be equal to k. Now, we have something called the integrated rate equation. The OpenStax textbook has a surprisingly good job of going through the integrals and the calculus and the derivation of this. We're not going to do any of that, but you do need to have this equation written down on a note card and for handy reference, okay? I'll show you a little bit more about this. So we have this equation, the natural log of A initial minus the natural log of A final, or at time t, is equal to kt. So what do all these things stand for? Again, the ln is a button on your calculator. You should be able to see the natural log. Don't forget to hit that button when you're calculating something, okay? A naught is the initial amount of the radioactivity, for example, or the drug concentration, or even the mass. AT is the final amount, okay? Again, it could be concentration, it could be grams, it could be radioactivity, like counts per second. And that's the final amount at time t, all right? K is the rate constant. That's the same K that we've seen in the rate law, all right? And T is time, and these are the units, seconds, minutes, days, years, okay? We don't use months that much. Usually everything should be written in seconds. That's a better way to just write things, but oftentimes problems will say days or minutes or even years. All right, let's go through an example here. So let's say somebody drinks coffee in the morning, and a cup of coffee that they're drinking contains 250 milligrams of caffeine because they're tired, they want to wake up, they've got an exam, all right? 8 hours later, how much caffeine is left in their body, okay? All that we're given here is that the half-life of caffeine is 5 hours. So we know that after 5 hours, half of that amount is going to go away, but 8 hours isn't a multiple of 5, okay? If the question was how much is in their system after 5 hours, we could just divide by 2 and get the answer, but we can't do that here, okay? So what we need to do is calculate K. That's the first step here. Now remember that the half-life is equal to log of 2 over K, and so we can solve for K. K is equal to the natural log of 2 over T1/2. And so if you plug that into your calculator, you hit the 2 button, I hit the ln, and then I divide by 5, and you can see how you get an answer in reciprocal hours. I'm going to jot this on the top left of the screen because we'll need it in a later step. Step 2 here is to use the integrated rate equation. Please jot this down on a note card if you don't already have it. It's handy for reference. Natural log of A0 minus natural log of AT is equal to KT, all right? And what are we trying to find here? We're trying to find the final amount of caffeine that's still in their system. So we're trying to find AT, all right? So we want to solve for AT. How do we do that? We subtract natural log of A0 from both sides. I'm showing you the steps here because if I just show the answer, a lot of students in the past have historically been confused. So I'll take you through the steps here. So let's subtract natural log of A0 from both sides, and we're left with minus natural log of AT is equal to KT minus natural log of A0, okay? So here we are. And now what we want to do is multiply each side by -1 to get rid of that annoying minus sign on the left, all right? And so I'm just showing it here. Make sure you distribute the -1 across the KT and the negative ln A0, and you get KT plus ln A0 on the right. And then what we want to do here is use the commutative property, right? A plus B is equal to B plus A. So I'm just switching those around because it bothers me mentally to have a minus sign added to something else. I like to write it more as a plus minus something, okay? Anyways, that is the equation we're going to use in this example and a couple other examples and many problems that you might solve, all right? Now what we want to do is plug in our values here. We'll take the anti-log later, but so again on your calculator you're going to enter 250, hit the ln button, okay, and then subtract and then use parentheses 0.139 times 5 hours, okay, and what you get is 4.83 on the right hand side. Notice how the reciprocal hours and the hours cancel, okay? Now, what we want to do is 4.83 is not the answer, okay? We want to take the inverse log here. So the way I do it on my calculator is right above my finger. If you can see it in this video, there's an e to the x key, all right? So on my calculator, I enter 4.83 and I hit Shift LN, and that does e to the x, all right? Here, I'm just showing it more thoroughly on the screen. You're going to do e to the power of 4.83. And that's equal to 125. And you might have an e to the x key on your button, e to the x button on your calculator in a different spot than mine. Now, what are the units here? The units are milligrams because the quantities are all milligrams, okay? So that's 125 milligrams of caffeine. So that right there is a half cup of coffee. That's a tremendous amount of coffee after 8 hours. Okay. I just realized I made a little mistake, and I oftentimes do this in my lectures to have students fix it for their notes. I put 5 hours here for the time involved in this, but actually the student is waiting 8 hours. So instead of 5, you want to plug 8 in there and then see what you get. All right. I do little tricks like that in my lecture. If you're watching YouTube for the first time on my channel, I apologize. All right. So the answer is not 125 milligrams. It's going to be a little bit less. How much? I don't know. You'll have to find that out for yourself, okay? All right, let's do example number 2. This is very relevant. You may have heard of this New Horizons spacecraft that was sent to observe Pluto most recently, and it's whizzing off somewhere out in the outer solar system. It contains 11 kilograms of plutonium dioxide, okay, as basically an energy source to provide electricity as well as heat, but it provides 245 watts of electricity. Now, plutonium This isotope has a half-life of 87.7 years, and we're just asking a theoretical question. How many years will New Horizons barely produce 10 watts of electrical energy? Okay, so what we want to do is calculate K once again. These types of problems will usually give you a half-life because that's very conceptually easy to understand. Oh, after 87 years, half of the material goes away, all right? And once again, we use this formula and we plug it in. We normally don't say the K, or the rate constant K, is equal to 7.9 times 10 to the minus 3 reciprocal years, because students have a hard time, even I do, conceptualizing that. What does that mean? Is that fast? Is that slow? What? All right? Now what you want to do, so I'm going to jot this down on the upper left-hand corner of the slide. What you want to do is go ahead and proceed onwards to use the integrated rate equation. Now here I'm just jumping in with that derived formula that I had from example 1, and we want to go ahead and solve for t. Okay, solve for t. So this is the integrated rate equation. We want to divide both sides by k, and we're solving for t, which is time here now. Okay, and we have the initial amount. We have 245 watts. The final amount is 10 watts, and we divide that by the rate constant, and we get a value of 405 years. Okay, so it looks like New Horizons is going to last a pretty long time. We probably will develop the technology to fly out there and replace the battery in 400 years. Example 3, we have radiocarbon dating. This should be carbon 14 on the slide. I apologize. It has a half-life of 5,730 years. So we've got a wooden flute that's excavated from a cave, and it's found to contain 350 counts per minute from this carbon-14 radioactive isotope. But a newly cut tree off to the side there has 845 counts per minute. And so we want to know how old is the flute, and this is how radiocarbon dating works. First, we calculate K as usual, so it's the natural log of 2 over 5,730 years, and we get this value. Okay, that's the rate constant. Once again, I'll jot it up in the upper corner of the slide here. Step 2, we want to use the integrated rate equation to calculate T. It's the time or the age of the wood we want to determine. So once again, time is equal to this equation here that you saw in example 2. We plug in our values, okay? The counts per minute is a source of radioactivity. It's a concentration, or it's grams. Either of those quantities work well in this equation. When you do this, you find the age of the wooden flute, 7,345 years. In summary, these are the equations you need to know in the main concepts. For a first-order reaction, rate is equal to K times the concentration of A. If you graph the log of A versus time, it's linear. The slope is equal to K. The half-life formula and the integrated rate equation should literally be memorized, or it should be written down on a note card and taped on your desk where you study. Okay? Thanks for watching. Please like, please subscribe. Have a great day.